Welcome to Subatomic Tanvi.
Hi, everyone.
So, you told me you are going to explain how I can tickle a friend in the next room without even going into that room?
That's not what I said. I was just gonna explain locality and realism in the context of quantum entanglement.
Oh, okay. Go ahead.
Okay, so locality suggests that an object can only be influenced by its immediate surroundings. Like, for example, if there's a ball on a table, if you just leave it there, it's not gonna move, it's not gonna do anything. But if you were to tilt the table, the ball is going to roll because you are in its immediate surroundings. But say you were trying to do the same thing from London. So, like, you're in London, but you're trying to move a ball on a table all the way in New York. It's not going to move because you're not in its immediate surroundings. And that also means that you cannot tickle your friend in the next room without actually going into that room.
Oh, how I wish I could.
So, locality is actually restricted by the speed of light.
So, you mean I cannot travel faster than the speed of light to tickle my friend?
Kind of. So, if you were to tell a joke to your friend on the other side of the room, if you just yell out the joke, they're going to hear you pretty much instantly. But say your friend was all the way on the moon, you would have to send them a radio message with your joke in it, which would take about 1.5 seconds to actually reach your friend, which explains that information also cannot travel faster than the speed of light, and nothing, not even your jokes, can defy that.
That's great. So, are we still talking quantum entanglement?
So we're coming to it. Quantum entanglement suggests that information can travel between two entangled particles instantaneously faster than the speed of light.
Can you explain with a simple example?
Okay, so imagine two entangled particles. You measure the properties of one of those entangled particles, and the other particle instantly knows and takes on a different property. So it's just like two magical coins. If you measure the properties of one of the magical coins and it turns out to be heads, the other coin instantly becomes tails, even if it's on a different planet.
Got it. So I guess quantum entanglement defies the concept of locality because we observe one particle, but the other one that's probably on another planet changes state with no influence from its immediate surroundings.
You got it.
Wow. Now tell me about realism.
Okay, so realism suggests that all objects have definite properties even when we're not observing them. It's like saying the moon is still there even when our eyes are closed.
But the moon is there even my eyes are when my eyes are closed.
Exactly. So quantum entanglement suggests that the particles don't have definite properties until they are observed. Just like in the magical coins example, the coins don't decide to be heads or tails until we observe them.
And the moon doesn't decide to be visible or not until I open my eyes.
Exactly.
Quantum entanglement defies all the logic ever known to humans.
I mean, quantum entanglement is just like rock, paper, scissors. It's just that the particles don't choose rock, paper, or scissors until we observe them.
But if things are so unpredictable in the subatomic world, how do physicists get to do any research?
That's where the Copenhagen interpretation comes in.
The Copenhagen interpretation?
Yes, the Copenhagen interpretation just suggests that. So basically, it's saying just forget about locality and realism and just focus on the probabilities because in the subatomic world, anything could happen. Anything. So the reality is always unpredictable. So just forget about locality and realism and focus on the probabilities because that's how we'll get to know more.
That's the deepest and the most profound philosophy I've ever heard in the last nanosecond. Thank you for another exciting episode, Subatomic Tanvi.
You're welcome. Bye, everyone.